and leaving the last class for questions, but I think this time we are running out of time. And I need to complete the syllabus. This is an important topic, so we will not have any questions, answer sessions. If you have any questions about any of the topic, you can stop by in the office and ask me. So we talked about a routing protocol which is based on link state. Every node has the entire information of the topology and they construct the routes. And we saw how we can remove few links so that we do not send too much information. So that was one way. Another is the distance vector protocol, which you all know. And this is hop by hop and what we call Dijkstra's algorithm. So this is based on the fact that every node doesn't have the information of the entire network. They just know their neighbors, and every node still can build some information about how to reach the destination. And this is called ad hoc on demand. So the previous algorithm was not on demand. So we talked about reactive and proactive. So do you know which one was the last algorithm? Was it proactive or reactive? Do you remember the last algorithm? Was it reacting to something or it was proactive? So the proactive algorithm decides to do something without, even when there is no demand, there is no request. And the reactive algorithm reacts only when there is a request. It was proactive because, right, so even if there is no demand from source to destination route, it will build the entire route for all the destinations. So this is on demand, this is reactive algorithm. Only when you need a route from source to destination, then only some actions will take place and you will find them. So that's why it's called on demand. These are the two papers which propose this algorithm. So if you want more information about this, you can look at these two papers, if you want. But otherwise the slide should be good enough. So the concept of this algorithm is really simple. If you know the distance vector algorithm, the big change is in this algorithm, the distance vector will run as it is. It will be a proactive algorithm. But in this case, only when there is a demand, you run the whole protocol. So it's purely on-demand routing protocol. A node does not perform route discovery or maintenance until there is a need. Okay. So if you have a network and nobody wants to send data to anybody else, there is no routing information exchange between any nodes. Right? Everybody keeps silent and they save their energy. Right? Only when you start your browser or something where you want to connect to the internet, then only it will start sending packet, it will build the whole route and then. So the disadvantage of this is, what could be the disadvantage? First packet, right? So when you want to send first packet, there will be long delay because there is no route from source to destination. So you have to find out the route and then after that everything is very fast. Okay? So for the first time there is big delay. Nodes that are not active, that are not on active paths do not maintain routing information. This is another advantage of this algorithm. So once you construct a route from source to destination, this is source, you construct this path to the destination, right? And this is your shortest path. Okay? And there could be many more paths. Right? If you find that this is the shortest, then all of these paths will remain silent. So they don't do any maintenance of the route. Okay? So again these nodes will save, all the nodes on this path will save energy. Okay? Only these nodes will keep on checking whether the route is end-to-end or not. Okay? So these will save energy. And we will see what this is. It uses a broadcast route discovery mechanism, so that we'll see in detail. And it uses hop by hop routing. So what does it mean, hop by hop routing?
At each node it is decided where is.
Right, so each node only knows the next hop. Okay, they don't know the whole path. So for example, this node in between A doesn't know that there is D at the end and there could be 1, 2, 3, 4 nodes. It just knows that what is the next hop, which will be B. Okay. So they only maintain a little piece of information, just the next hop. So that way it is again efficient. And there are other protocols like this. There is one called dynamic source routing, but that is different, and we will not talk about DSR routing. Okay, so we just talk about OLSR and POD. So how would you now? So you all know the Dijkstra algorithm, right? At least so we refresh what Dijkstra's algorithm is. So if you want to do it on demand, what will you do? Can you think of how will you modify Dijkstra's algorithm so that now it becomes on demand? So what is Dijkstra's algorithm? Can anybody just tell me what happens in Dijkstra's algorithm? Let's forget about Dijkstra. Let's take, you have a routing algorithm and you want to make it on demand. What will you do? That's the simple question. You have one routing algorithm and you want now to make it on demand. What would be the obvious thing to do? Make it on demand.
Broadcast messages when there is a need to create a path.
Right. So let's say my function is this routing underscore algorithm, right? So this is my code. This is my function, and it returns me the entire, not entire, but so I can give him the destination address tree. Source is of course myself. Okay. So source is my own ID, and I can give this algorithm destination D, and I can call this function and it will return me the next hop. Okay. So in standard routing algorithms, what we are doing is you will have a for loop for I is equal to 1 to capital N, and we will use this algorithm, right? Something like this. So what it will do is it will go through a list of all the nodes in the network and it will find out the next hop for all the nodes. Okay. So this is how the routing algorithm will work. Now when you make it on demand, you don't have this. Only when you find the need that you want to reach a destination D, you will call it. It will give you next hop and you will stop there. Okay. So you can take any routing algorithm like this and just make it on demand. So first thing in any routing is find out your neighbors, and that's a very simple thing is the hello message or neighbor message or something that you find who are your neighbors. And this is a broadcast message so that everybody around you will get this. And then another thing is the sequence number. So we'll see what the sequence number is. And one thing we will do is there will be two pieces of information with every node, and these are the counters. And this will look very simple to you now, but there is a lot of challenge in finding out what should be the counters maintained and how to maintain it. So one is the node sequence number and another one is the broadcast ID. So broadcast ID is whenever I send the broadcast, I will give him a counter value 1, okay, then 2. Every time I do a new broadcast, it will have a new ID, and every time I send out a packet in that broadcast, I will have a sequence number, and we'll see how this is done. And so these sequence numbers are tied to this. Sequence numbers are assigned to routes and routing table entry. And can you guess what these sequence numbers are used for? There is some standard use of sequence number in the network. But what would be the use of this sequence number? For parallel. So when we use any number, anytime in any algorithm, sequence, right? So you want to find out who is early or who is before and who is after. right? So the reason for giving IDs and everything is to put them in some order. So this is the same use here. So if you know one route to the destination with sequence number 10, and then you get some information and you say that that sequence number is 11, you will forget about the old route and you will use the new route. Okay. So the use of this is, it is to superset state cache routing entries. So if I have a path from source to destination, I have path number 1 and then I have path number 2, then I will delete this from my routing table and I will update it. And you will need these numbers to find out which is the early information and which is the old information, new and old. Whenever this number is bigger, it's a new information. Okay, and you will forget all the old information. And this is necessary because you will get so many packets coming here and there and you don't know which one to use. So to eliminate the old packets, you will use the sequence number. Same thing for the broadcast technique. Whenever you broadcast something, and so what is the use of broadcast? I send the packet to everybody and everybody will send it to their own neighbors. I have once forwarded one broadcast, let's say with ID 10, and if I get another packet with same broadcast ID 10, do I have to forward it again? No, because I already sent it, right? So there was a new message coming in with broadcast ID 10, I send it, I get another copy of it, let's say a redundant copy of it, I don't have to forward it again because I already forwarded it. So let's look at directly the example. Okay, because otherwise if I keep talking about these items and numbers, it will be really confusing. So let's look at the animation. We're using the same network that we used before. 1, 2, 3, 4, 5, 6, 7. This is how the connectivity is. And our idea is now node 1 needs to send a data packet to node 7. Here to here. Okay? And nobody knows any routes before this. Everybody is silent. They don't know anything about the routes. Except for the fact that node 6 knows the current route to node 7. So node 6 knows. How would node 6 know the route to node 7?
Because it has 6 and 7 are neighbors.
Direct neighbors. So because of the hello messages, they know who the neighbors are. Right? So you don't have to go all the way to the 7 node. If you reach node 6, 6 knows that it is directly connected to 7 and it can send that information. Okay, so this is true. No other route information exists in the network related to node 7. So that means 1, 2, 3, 4, 5 don't know anything about 7. Where 7 is, who is its neighbor and so on. Only node 6 knows. Okay. So can you think of an algorithm to find out just the route between 1 and 7? I am not interested in knowing all the other routes. Also, other nodes 2, 3, 4, 5 are not interested in finding route to node 7. Only one is interested. So what will one do?
One will apply the routing algorithm.
Right, but no, so we are finding out what that algorithm is. For now.
One will ask 4 for the route, 4 and 2 for the route to 7.
Right. So when we contact, so he doesn't know what is the route to 7, what is the next hop. Forget about the route, he doesn't know what is the next hop to 7. So it will send a broadcast saying, I want to find route to node 7. Okay? So the broadcast comes here and here. What will node 2 and 4 do?
They will send the broadcast to all these neighbors.
Right, but before that they will check whether they know the route for 7. They say, I don't know. So I can also do a broadcast. So the broadcast comes here, broadcast will come here, broadcast will come here, and broadcast will come here. Okay. So you see the same B message now is here from 2 to 3, and from 4 to 3 is also connected, so it will get a copy from 4 to 3 also, 4 to 5 and 4 to 6. Now let's look at 3, 5 and 6. Let's start with 3. What will 3 do?
3 will send it to 5.
Right. But before that, there are two things. One thing is, there are two messages, B and B here, coming from both the directions. Okay. So, and we will assume that everything happens internally. So two things cannot happen at the same time. Our clock is such that two things will not happen at the same time. So either of these two will come before. Okay. So let's say this comes before. For now. Okay. In mathematical terms, without loss of generality, this will come first. Okay. So what will 3 do? So this is not there yet.
So 3 will send it to 4 and 5.
Right. So 3 will send it to 4 and 5. And now this one comes. What will 3 do?
Send it to the
Triangle, there's X of 4.
No.
2 and 5.
So this is now not useful, right? So we have already sent something with the same content to everybody. I get another copy of this, I don't have to send this to everybody again. And that was the use of broadcast ID. So this broadcast B, capital B, will have a unique ID associated with it, and whenever 3 compares this IDs, it will be same. So it will not send this message again, and that's why there is only one copy coming from 3 to 5, and it will not send it to 4, because again, so this copy is not sent to 4. And same thing will happen at every node, even 4 will not re-forward it. Okay? So this happens throughout the network. So let's look at, so we have looked at 3, 4 will send it here, here and here, and 3 will send it here and here, and now there is a copy at 5 and 6. Okay. So what will 5 do? So 5 will also forward it. Okay, so 6 will get a copy, but 6 has already received one copy from 4. Okay, so this comes first, and this comes second. Okay, so let's see what will 6 do now for the first copy. What should 6 do? So the message is asking for a route to node 7. What should 6 do?
one hop connect, which should reply one hop connect.
Right? So it knows that somebody is looking for, in fact node 1 is looking for destination, a path to 7, and I know it. So what should I do?
Send it to both its neighbors.
No, only one neighbor through which
Right.
first got the copy.
So it can send it to all the neighbors, right? There are multiple, but we are assuming that this comes first. So it doesn't know. Is there a point sending it to 5? 5 never asks for it, right? So B1 comes first and then B2 comes. As soon as B1 comes, 6 says, okay, I know the path to 7, right? And who is interested for me? It is 4, okay? So it doesn't need to send a reply. We'll say it's a reply to 5. It can send it to 4.
But after like from P2 comes then 6 can send it to 5 because 5 is also asking.
Right. So there is a question. There is a question there whether to send it to 5 or not. But right now what we are seeing is only 4. We are getting first copy from 4. And we still need to answer whether to reply to 5 or not. Okay. And that is an algorithm we have to decide. Okay. But 6 can send it to 4. And 4 can, what will 4 do? So this is a reply message now. We say it's a reply to 4. And then what should 4 do in this message? Right, so 4 gets a reply from 6. What should 4 do to that message? Whom to send it to?
1.
Why 1?
1 and 3.
Why 1 and why 1 and 3? And why 1 or 3? We'll see how the combination.
It should send to the one with whom he has got the price.
Got it. That's a good point. So we can, if we assume that from 4 we got it first. Now we can't really say first and second in the network because we don't have a clock. I never defined a clock. I just have counters. So in terms of counters, how can I compare?
If we got from 3, we have 2 hops, but from 1
Right.
we receive the
So it's not the count. So it's not the time now. For second, it's the hops. Right. So 4 knows that this is 1 hop from me, and this one is 1 hop. So how many hops is this? 1, 2, 3. But how does it know that 1 is 3 hop for me from this one? Does it have this information? So we will need 2 values for hops. This is 1 value and this is second value, right? And then it can compare and send it to 1. But how does this is obvious because this is directly connected. How does it know it's 3 hops?
It cannot know anything. See, but it cannot be balance for 1. It has to be greater than 1. It has to take use because 4 Maya 3 are taken.
Right. So that's good point. But I can say in this algorithm or this, I can actually say it's 3.
first one ask for hours, then 2 hours, then 3 hours. So
Right. So how do you call it now? We have to write an algorithm.
Define a component in the message. And
Message
send
itself.
the message.
Right. So when you send a message, right, this is your message. You can put hop value here, right? So when one sends this broadcast message, it puts hops is 0. When it sends to 2, when 2 receives it, and when 2 forwards it, it will increment the value of hops in that message itself. Right? So when this message comes from here to 2 to 3, and then to 4, it gets incremented by 1, 2, and 3. Okay. So the message now is not. What is the message content now? So this is my message. Can you tell me what will the message contain?
number of hops.
Hops. Okay.
Destination. Source.
Source. Anything else? Broadcast ID. Okay. So this is the content of the message, and you will increment the hops whenever you forward it. And when you receive it, you decide by looking at the source, destination, and broadcast ID combination to decide whether to broadcast it again or not. Right? And what will, so this is the broadcast message. What is the reply message? There is a reply message also going. What the reply message contain?
Hops.
Does it need to contain hops?
Yes, like how many hops the destination is from me.
Right. So first of all, you need to uniquely identify this message. Right. So you need some kind of an ID.
Reply ID.
Reply, you can use the same source, destination ID. Right. So you can put the same thing here, source, destination, and broadcast ID. Right. So that's, and then you get the hops. And how do you, so routing table contains two information. Destination, next hop, and number of hops. How will you get the next hop for routing table?
Suppose if one gets message from 4 that this is the route to 7.
Right.
Whatever is the shortest that
Right.
one can know it is.
Right. So 4 gets a reply from 6. So 4 will say my next hop is 6. 1 gets a reply from 4. So 1 will say my next hop is 4. Okay. So this is how they will know the next hop also. And then they will fill in all this information. So let's take a movement here. So I have described you almost the entire protocol. But we'll go through this again slowly. Any questions before?
Sir, if we are saying we can convert endpoints into dynamic on-demand algorithm, then why can't we convert the last one which is studied for low endpoint?
Alright, so I was exaggerating here. Not any algorithm. We want to have something which is optimal for on-demand, right? So any algorithm which will be just giving me source and destination. Anything else than this will be not optimal, because I just want the destination D. Any questions on the algorithm? There are a lot of things happening. There are lots of IDs, hops, and so on, and how the things happen. And we just described it in English. But if you understand mathematically what's happening, that is more important. So let's go through this again. Okay, so let me just erase everything. So this is our network, and we want to construct a path between 1 and 7. 1 is the source, and this is the destination. Since node 6 is the direct neighbor of node 7, it directly knows that it is 1 hop away. So if anybody asks 6, what is the route to 7, it can reply something. Okay? Otherwise it has to go all the way to 7. Now what's happening is, 1 will first ask to 2 and 4, and to ask it will send a broadcast message saying I need to find a route to 7. Do you know it? If they already know it, they will reply back, and wherever you get the first reply, first as in the number of counters, you will set it as your next hop and you have the route. If they don't know it, they will forward this message to again everywhere in their neighborhood. Right? Using the broadcast ID, you can eliminate the repeat broadcast, because you will get a copy, so 3 will get a copy from 2 and also from 4. And when it gets it from 2 and it forwards it, it doesn't need to work on the copy which is received from 4.
Why does it need broadcast ID? Because already source the destination of same thing, you can just.
Right, so why do you need an ID? You establish a path, and then something happens with the path, and you want to reconnect to that node. So what you are saying to the network is, this is my new request. Forget about the, if you know about the old request, forget about it, because that path does not exist anymore. Right? So whenever you want to find a new route, you put a new ID into this. Right? So it's a new question. That is why the ID is necessary. And so these broadcasts will come all the way to 6. Since 6 knows the path, it will reply to the source, but it doesn't know the route to the source. So it will reply to the node from which it gets the earliest of the shortest, which is node 4. Okay, and then it will forget about 5. Now there is a case. If it replies to 4 and it receives something from 5, there is a possibility that it can reply to 5 also. Do you know how will that happen now? Or let's reverse it. Let's say these nodes are very fast, and their processors are very fast, and they forward it very quickly. So it comes here B, it comes here, it comes B. Right? So this path is very fast, and for some reason 4 is very slow. So what will happen now? So 6 receives a broadcast message from 5 before. What should it do? Is the question clear?
It should check that after how many messages contains how much number of hops, and the least number of hops it should consider that. It would receive a packet from 4 message from 4 also.
No, so right now it has not received anything from 4. The first copy arrives from 5, and that is what it does. What should it do? And our goal is to minimize the number of hop counts. It's not about how fast these nodes are. We just want to minimize the hops.
It should have some delay for accepting.
Right? So that is one way. What you can do is, at 6 you just wait. You don't reply immediately. You wait to give the reply back. It's like you think about it, and then you get back to 5. Okay, that's one solution. Another solution, if you don't, so the timeout has issues because there could be problems, right? Even within that timeout you don't receive anything, you will reply to 5. So let's assume the worst case scenario. Worst case scenario in this is you still receive something from 5, right? You time out, you reply back to 5, and after that you get something from 4. What should you do?
It should then reply to 4 and 5. Then 5, I have dismissed this path and 4 and 5.
So it will reply to 4 for sure. Does it need to reply to 5 that I have dismissed it?
It should.
Why?
Because then 5 would have transmitted this message to 3 that I am connected to 7, and 3 would have then connected to 2 and 5. So we need to cross that path, because before getting message from 4, it would get the message from 2. 1 would get the message from 2 that I have a path.
Right. So, but there is one thing. So from 6 you reply to 4, and this message comes to 1. Okay? They come very slowly, but they do come at node 1 finally. Now 1 will use 4, and 4 will use 6. Okay? So this path is established end to end. Do we have to worry about this path? Why? No, that not understand.
They are fast processing wrong
No. So route has been established, that's fine. But 1 will just send it to 4 now. whenever one learns that 4 is supposed to be my next hop, it will remove the entry in its routing table. It will not put 2 here in that routing table, right? It will put 4 here, and similarly 4 will use 6, right? So one will never send anything to 2, and it can just let that route get perished or destroyed, right? It will not maintain it. It will not try to do anything. So they will just forget eventually, because these nodes are using the shortest path. So we don't need the timeouts now. What I'm saying is we have the concept of timeout, but we just forget about timeouts. Whenever I get a message from 5 to 6, 6 will reply to 5, and 5 will so on here, it will come here. When you get this message from 4, you will also reply back. The reply will come here to 1, and 1 will do the necessary things and will use the shortest path. What I'm saying is you don't need the timeout. You can have the timeout, but it's not required, because in any case you need to have a comparison of hops and take the action. So this is how we can simplify our entire protocol without having any timeouts.
It's not based on outcome or the source. When you choose the path, you have
So,
why does how does S source this?
okay, how does S know? So this route, how many hops is this?
So it's based on outcome.
Hop stop, right? So whenever one receives a reply from 4, it says it is 2 hops away from me, and this is 1, 2, 3 hops away. So S knows that this is 2, this is 3, right? So I should use this one. So it will change its routing table here, put new entries, and will keep using that. And this route nobody is using, so it will just die. And you don't need timeouts. The timeout is required in network only when you have a possibility of, when is the timeout required in networks? What happens because of condition? Whenever there is a drop, whenever you drop a packet, right, then you have to retransmit. And that is where you have a timeout, because now you don't. So this is an impossibility. There is an impossibility result in distributed systems that you can never find out whether the message is delayed or dropped. So that's where you have a timeout. And when you have timeout, that means your message is dropped and you want to retransmit. In our case, we are not assuming any drops. Right? The message will come, it's just delayed. And if it is delayed, it can delay any time. Right? So you don't need a timeout. You can just use both the messages and take actions. So this is going a little complicated, but it's the protocol here. Don't worry about timeouts and all of these networking things. So main idea is to get hold of this protocol. Any questions on the protocol? How it's happening, which messages are there, and so on. So this is the message. We already derived it. So forget about this. There is a hop count. Then there is a broadcast ID. There is a destination address. There is something called a destination sequence number and source sequence number. So we'll see what this is later on. But the rest of the things are very easy. And these are the standard things. Type, flag, some reserved. So you see all this in most of the IP packets. So it's similar. So this was our route request message. Whatever I was calling broadcast is basically a route request message. And you send it to everybody. So sequence number, the job is to indicate freshness of the reverse route. How fresh this reverse route is. Destination sequence number indicates freshness of the route to the destination. So you can go, so we'll see what this exactly is doing. Every neighbor receives a route request and returns a route reply or forwards the route request to everybody. This we have already seen. And source ID, source address and broadcast ID uniquely identify the route request. So whenever a source generates a new request message, this combination is the primary key in database terms. This is how you will uniquely identify. If you see a repeat of this, you can immediately know that this is a repeat telecast.
For how much time this packet is maintained as with a particular route? you were following it, and you were saying as in the packet won't be forwarded into 4 if we have received it from 4 otherwise already. So for how much time it would be maintained so that it can be checked?
Right, so this is maintained permanently. Permanently. So you maintain this combination. So this is, so you don't have to maintain all the values. Like what I'm saying is, once you receive something from source comma 1, okay, this is what you maintain. Next time you get source comma 2, s comma 2, you will maintain s comma 2. You don't have to maintain the whole serial. So you don't have to save everything. You just have to save the latest value.
So for one source we have a one
One
product.
value, right? That's it. And you will maintain it because whenever next time you receive it, you know whether it's a repeat or not. That's it. For node you will maintain one value, and this will uniquely, because another node S dash will also have 2. Right? So this is different. This value is different from this value. So from S power, in our case this is 1, right? Node ID 1, and I have received 2 broadcasts from it. And this is node ID, let's say 2, and I don't have any other broadcast ID, right? Or it could be the same one, 2 also. So this will uniquely identify. So it's like I am sending you questions, question number 1, question number 2, and then another course which is also giving you questions. So the unique ID is the professor's name and the question number. Right? Just professor name is not good enough and just question number is not good enough. So it's like that. And this is what you will use to discard the duplicate messages. So the protocol message is whenever, and we looked at the hop count value in the message, node increments the hop count value inside the message and then only it forwards it. So this is how at this final node you will know how many hops is there, and then you can compare. So remember 6 is going to compare between 2 request messages, right, from 4 and from 3 or 5. Right? So this is what it does. A node saves this information to implement the reverse path. So locally what does it save? Neighbor that sends this request message. So you know the reverse path. So when you're broadcasting, you actually is keeping one pointer in the other direction. So just like a linked list. Right? When you have a linked list, you can have double linked list like this. Right? You send the packet, but you also maintain a value or a pointer back. So you're doing the same thing in this network. Whenever you forward something, you also maintain a back path so that you can reach the source. You maintain destination IP address, source IP address, broadcast ID, source node sequence number, and expiration time for the reverse path. Right? Because if the destination is not there at all, you want to send data to 7, but 7 does not exist. For some reason, it has gone out, has switched off. So you have to forget this information after some time, right? Because the whole thing will be dropped, and this is what the timeout is here. So after that, you will forget everything because you don't want to remember this for the long time. Any questions with this? This is easy. So this we have already seen. So let's go through the example with. So node sends this information. Source address is 1, destination address is 7. Broadcast ID is my previous ID plus 1 because this is a new broadcast. Source sequence numbers is again plus 1, and destination sequence number is last destination sequence number for node 7. Okay, so there is a unique number for every node, and this is different from broadcast ID, and we'll see what this is. So this is what you send to neighbors. The neighbors will forward it. You see, you send it to 2 and 4. And then they will also forward it. 2 sends it to 3, 4 sends it to everybody, and 3 gets a duplicate. So this is a duplicate. One copy is coming from here, this is the duplicate. Node 2 and 4 verify that this is a new request. That is the source sequence number is not still with request to the reverse route to node 1. And they will forward it. And they will update the sequence number and increment the hop count. Okay, so they change the hop count in the message and they update their sequence. And forwarding it goes to 6, and 6 will verify the sequence number is less than or equal to the destination sequence number it has recorded, and 3 and 5 will forward the request packet but the receiver recognizes, so 6 will recognize that it's a duplicate, it will ignore it, and rest of the numbers also. So 6 will reply back. Reply message contains again the same things: hop count, destination address, sequence number for destination, source address, and lifetime. You can ignore the lifetime value, but basically the same things as you were talking about in the reply. So intermediate nodes propagate this reply for the source towards the source, because everybody has a back pointer. So when you send it, you will send it to the back pointer, and it will come finally to the source. These packets are discarded unless the destination sequence number is higher than the previous. So you have, this is stale information. So if this information is stale, you will ignore it, or you have a better path. Hop count is smaller. So there are two things. One is the stale information or new information, and number of hops. Eventually it will come to the source, and source this way will have the path. So for example, in here 6 goes to 4 and 4 goes to 1. The hop count will keep increasing in this case. So you will increment the hop count, and so this is how one will come to know that it is 3 hops away from 7, because everybody will put that hop count value there in the reply. At the end, one will have the routing table entry of 7. Destination is 7, next hop is 4, and it is 3 hops away from 7. And that's it. So this is the protocol. Right? So this is where you have the routing table populated for one ID, 7. You keep using this. What happens if there is a change?
Forget the path and we
But how do you forget? How do you know that there is a change? Packet loss. So if something drops out, you will know that there is a packet. If there is a shorter path, let's say this thing happens, what will you do?
The table would be updated as in
Very
it will have the direct link to 7 up.
Right.
The board will also know the root to 7.
So this is starting from 1.
4 will reply as in
Right. So 4 can take some action. So one thing is, one will not, if it is using this path, one will not proactively do something. Right? Because it says this path is good enough for me, it will keep sending. 4, when it detects something, it will change its whole routing table,
send a message.
send something to 1, and it will know that the hop count is only going to be less. Right? So the only change you need to do here is this one. You don't need to change your next hop. Right? So this locally happens at 4, and it will send back a new reply message, but it will not go in there. For now, just assume that such a thing does not happen. So the maintenance wise, we maintain something whenever there is a failure of periodic hello packets. That means a link is not existing anymore. If any link breaks down on the route, you don't see the hello messages, and you have to do the maintenance of the route. Failure or disconnect information, failure of transmission of packet to the next hop. So anytime something fails, there only we do the maintenance. Then what do you do if anything fails? Can you think of a solution? If your route fails, in this case, what will you do? Let's go to this case. So this link is broken, and 7 is mobile, so it goes here and connects to 5. What should we do? Right. So 6 doesn't know now what to do with the packet. It knows that it is not hearing hello messages from 7. So it can send a message to 1 saying I don't have a route to 7. So you delete your entry, and you can then do the same algorithm again. And then new algorithm, when you run that new algorithm again, you will get this new path. Okay. So this is how you maintain the route. So node 6 issues a route error packet, RERR, indicating the broken path, and the error propagates back to node 1, and node 1 can then discover a new route. So you will re-execute the same thing again, and it will find a new route. So this is where the maintenance happens. I am not seeing this extra case of addition of links. So we will only consider deletion of links. So the advantage of this is you don't have to maintain so much information. Not everybody has to keep sending messages and so on. So this is mostly used in mobile networks. As so the algorithm that I showed you before, OLSR, it's not used highly. This is the highly used algorithm because you just connect to the one where you want to send packet. There will be first delay, that is fine, and then you keep sending the packets. You can do something which is cluster based. So there is a hierarchy of algorithms. At one stage, so do you know in internet what is the hierarchy? There is some. Have you heard of a term called BGP? Do you remember the term called BGP? Border Gateway Protocol. So this is the protocol executed at a very high level between the internet service providers. For example, Tata, Reliance, when they talk to each other, their routers, they execute this protocol, BGP protocol, and underneath we execute some other protocol. Right? So this is hierarchy. Same thing happens here. You can construct clusters of nodes where you execute one protocol, and inside cluster you can execute another protocol. So in BGP it's typically link state protocol. And inside one border gateway, inside one internet domain, you can use the distance vector. Same thing here. At high cluster you can use OLSR, and inside the cluster you can use AOD. Right? So this is similar to IP, and you can use all this hierarchy. So this is how it will look. So within this cluster, so for example, IIIT will use some protocol, NSIT will use some protocol, and between IIIT and NSIT we can have another protocol. This is another way of doing it. So today we will finish early. So layer 3 routing is needed to do anything at wireless mobile networks, right? You cannot do everything at layer 2. And these are multi-hop protocols, so you actually send it over multiple hops. But you don't have multiple interfaces, just one wireless card and you do the broadcast in the network. The problem is wireless, because wireless has lots of path losses and mobility, right? Continuously mobile. And that's why we have two types of protocol, reactive and proactive. So the reactive protocol is activated only when there is a need. For example, AODB. Proactive is activated all the time, like OLSR, and you continuously update your apps. Still, this is a very niche application. Not everybody. So, for example, your laptops don't use this protocol. Right? You typically, if you want to send data to your friend laptop, you will connect to Wi-Fi and then send it or through Bluetooth or through USB stick. It's not a very common thing to do, but there will be scenarios where this will become more and more common. But right now, it's very rarely used. So that's it. So any questions about not only this, even in all the syllabus that we have covered, or
Saying this is that in the slide says that in theory it's in the cluster and OSR is within the cluster.
it could be any way. So what I was saying is, you don't have to use one routing algorithm for everything. For example, OLSR, every node has the information of the entire network. Right? So that's something you cannot use for the very big network. You can use it for a very small network. For example, within IIIT we can use it. But then if you want to combine all the laptops of NSIT and IIIT, we will not use that. So in that we will use maybe AOD. So depending upon what is the scale of your network, how many times you send packets, you can use either one of these, and at multiple levels in hierarchy you will use different ones. So in the final exam there will be questions on this. I will not typically ask you the right protocol action. So what is this protocol describe? I might give you some examples, and then you have to follow some steps and find out. Or there could be some messages that I can show you, and there could be some errors which you have to detect. So you should be able to understand what is the routing protocol exactly doing, and how it is doing, and how it is handling the problematic cases like mobility, laying down, and so on. What is the use of the sequence number and so on? What is the use of opcounts? How it is used? So that's very important. Again, in mobile IP, we have covered few things about Wi-Fi, 82.11. So all of those things are also important. Bluetooth, something. And we also covered GSM networks. Right? So that is important. And also the 3 presentations. So any questions? Yeah. So I said Symbian OS, right? So let me write it down for myself. Goes from one network to another network, right? So that is the difference. Rest of the internet is static. Only one node moves from one area to another area, and how to still maintain the connection and send packet. So that was a different case of mobility. This is a different case of mobility. No, you don't need to do in detail the experiments there. You just need to know what is they are talking about as in concept, what was the problem, and what is the key thing in their solution. If there is a solution, there is no solution in that. But no, you don't. I am not going to ask you details about experiment, how it was done, and so on. It's mostly conceptual questions. If you understand the paper, that's good.
The 3 presentations which you have selected, will you be giving questions only from the presentations, or will we have to or anyway on the paper?
Okay. So typically you don't have to go unless you haven't understood anything and you can go to the paper. So in presentation, if you just look at it and you understand, that's good enough. Just like I do. I show you presentation and never tell you, okay, go to this book chapter and so on. If you understand the presentation, that's good. You don't have to go through it.
In some topics which are not covered in the presentation.
No, it will not be covered.
It won't be covered when you work after.
Only thing which is presented, that's the only thing. Because it was not the paper that I selected, it was the presentation that was.